In the tutorials, we did 2 tutorials. The first one was a tutorial where we simulated just an algae organism, so just a linear algae organism with 2 simple rules, which is taken directly from the classic L systems examples. So with 2 types of cells, A and B, and it grows through the B cell. So that was a first introduction to graph rewriting. And then we did some snowflakes, where we have some 3D structures. And that's where we stopped. So today I want to go through a series of tutorials, which are all interconnected, where we start with a simple descriptive model of a tree. A fake tree is not a particular species, it's not calibrated to anything, but at least it looks like a tree. And then in the following tutorials, I will add more and more complexity. So I will add some sourcing relationships, some line interception, some radius efficiency, etc. So that then you get a flavor of how to build up an FSPM in VPL. Okay. There's a lot of text, but I'm not going to go through all the text. The key things here is that because now we're simulating a plant, we are going to define different types of nodes. So in the graph, we're going to store different types of data, okay, representing different types of organs or points in the topology of the plant, okay. And here, there's always going to be a confusion with node. So I will cover that because it actually does a very nice thing about VPL, which are the namespaces, okay. So let's start running some code. So as always, we load the virtual plant lab. Hopefully it works on my laptop. I haven't tested in a while. And the first thing is that, as I recommended last time, whenever you define the data types for your model, I recommend that you put them inside a module. Strictly speaking, you don't have to do it like this, but there's, let's say, a limitation or a feature in Julia that you cannot redefine your modules in the same session. Sorry, your data types. You can redefine functions, but not the data types themselves. But if you put in a module and you import the module, then you can do it. You can change them and re-import the module. So inside the module, I call it tree types. You can call it whatever you want. Then we define the data types that correspond to these organs or points in the model. So it's a very simple FSPN with all the elements of a phytomer. So you have an apical meristem, you have a bud, so that's like an axillary bud connected to a leaf. You have the botanical node, which is different from the graph node. Okay. Then you also have a node for the lateral bud. So when the lateral bud emerges, then you have a branching point, let's say. I call it bud node, but maybe branching point could be a nicer name. And then we have the organs that would have some...
Why do you need that?
Huh? I don't know if you need it, but I like to have it for the branching point. You could also have just 2 internodes, you know, one for the branch and the other one. But I mean, in this model, it doesn't really do anything.
It's a bit like,
Yeah, exactly. You could use it as the starting point of a branch. Yeah. But I did it more for consistency, like a meristem, when it starts growing, a new internode leaves a node behind. But yeah, I don't think you need it. And then the internodes and the leaves, which will actually have some geometry. Okay. Now, what you notice here is that I use import virtual plant instead of using virtual plant. So when you use import virtual plant, then it will not import the names in the package. So whenever you refer to a function or a data type in virtual plant, you need to prefix it by the name of the package. So in that way, you can have your own variable called node, and then there is the node from VirtualPlan, so the botanical node and the node in the graph. You can use what's called an alias, which I didn't use here, but I can show you. In the import statement, you can say as VPL, so of course my computer already knows. And then you can use VPL instead of VirtualPlan Lab, for example. This alias can be whatever you want, right? Yes, because you have a data type called node, and there is also data type or an extra type in this case called node in VPL. Yes, exactly. Yeah. So when you use using, then you import what we call the public API in other languages, so all the exported functions. And otherwise, you just import the module. So VirtualPlan is basically a module. The disadvantage using? No, just that you can get these name clashes. Yeah. You could. No. In terms of performance, it doesn't matter. Some people recommend, like, for example, inside a package, a Julia package, I will not generally use using. I will either import the package or import specific functions. You can also import specific functions. You can say import VirtualPlan Lab node. In this case, it doesn't help us. But if you only want to use a particular function or data type from a package, you can import that one specifically, right? I mean, if there's a problem, Julia will let you know when you try to run the code. But yes, indeed, it's also considered good practice. It's just that it's a little bit, it feels less dynamic, right? So there's always this tension between, quickly writing your code and making it safer, and later we'll see run faster. That always takes a bit more time and more care. Okay. But I'm showing you just different options. And now, in these data types, I don't store any data. So this is similar to what we were doing with the algae example, because there's nothing to compute on those organs or points in the graph. For the internet from the leaf, then we have some fields for the dimensions of the organ, right? Which later we will use to generate the geometry. Now here I'm also introducing a new concept that I did not use in the previous two tutorials, which is what's called a graph level variable. So you can store data in each node of the graph, okay? And that's what you define with these data types. But you can also store data in the graph itself. So this will be like a plan base in many of our FSPM. The difference is that you can always access this object from anywhere in the graph immediately. You don't have to write a relational query to navigate the graph until you find the plan base. You can just say graph data from within a rule or query, and it will immediately give you this information. Okay. And yeah. But remember, each plant can be stored, as I will show you later, each plant can be stored in its own graph. And each graph has its own copy of this object, and you can update it separately, right? So yes, yes. You could do it. You could have multiple plants per graph if you want to, but that's not ideal. And in the future, I actually want to have like a true multi-scale graph where you have this, because now it's just at the plant level, but in the future, I want to figure out how you can store information at the branch level using a similar approach, right? So that you don't have to write this relational. Because right now, if you want to store information at the branch level, you have to use like a branch-based node. Huh? Or a path node, yeah. But the idea is to avoid all those expensive relational queries by having like a hierarchy of scales within the plant. But that's long term. But that's where I'm heading, basically. Yes. What I was thinking of when coming up with these graph level variables that you store here parameters, especially if they vary across plans, okay? But also things that vary over time, like state variables that are defined at the plan level. Like, for example, if you have a single pool of assimilates, like a global assimilate pool in many of our models, that will be stored in the graph level, right? Or if you want to store the age of the plant in thermal time, you store it in this graph level variable. Okay, so run this. So this is up to you. So this can be any type in Julia. What will make it a graph level variable is that we will store it in a specific place. So when you create the graph, there you decide what is a graph level variable.
See that here? What do you have?
No, you don't see it yet. It's later. So
Okay. Yeah,
you first define the type, and then you create an object of that type, and then you store it in a graph. Yeah. So sorry, it's always a bit backwards.
3 params.
Yeah, you can call it whatever.
Okay. With the base dot at
Yeah, sorry. So this is just so this is a Julia thing that allows you to have default values for your types. So that when you create a leaf or when you create a tree params, you only need to specify those fields that you want to change, right? So if you want to rely on the default values for most parameters, then you only specify the ones that you want to change, right? And that's what you get with this base key WDEF. So it's a keyword definition, basically.
And the graphical level variable, then you can see that 3 parameters is not a structure because you didn't give it the node.
No, so there are both structs, which does the Julia word for class or type. The difference that leaf inherits from graph node, right? And that means that then you can use it to construct the graph using the syntax. So I know that some of these things are forgotten, but I will show you again how to do it, right? But so this you always need to add to any type that you want to use inside the graph. And so your leaves, your growth organs, visible organs, these kind of things, always inherit from the graph node. But this is entirely a user-defined object. This can be as complex as you want, basically. Okay, so we create the module and then we import the module. So now we can access, and I use import, which means that instead of using, so I use 3 types dot whatever if I want to extract a name, which by the way in Java it works the same thing. If you import a module, you need to use the module to access the function or the class.
Yeah. You define the module.
Yeah.
You don't need to import it anymore. It happens in the same script.
Yeah, well, technically I'm importing when I say import 3 types, but yeah, it happens in the same script. Yeah, because Julia is a dynamic language. So the code that executes it's like R. As you run the code, that is the program. If I run this code in a different order, then I technically have a different program, right? So it's just like R or Python. Okay, so remember that if we want to have geometry, so we want to generate a 3D representation, we need to define methods for the feed function. Okay, so it's a feed exclamation mark function, and they always look the same. So you always have a turtle, and then the data type for which you want to define the feed method. And then there's a third one called data. And this data is actually the graph level data that you store, right? So like I explained last time, you define this feed function, but you don't use them directly. VPL is going to use them for you, right? So the idea is that when you create a scene, it will generate the 3D geometry for you automatically by calling the feed function. Okay. So inside, we saw last time an example for the snowflake. That was relatively simple. What we see here for the internode and for the leaf is a little bit more complicated than what we saw with the snowflake. So first, I have a rotation of the turtle around the head. So this is basically rotating around its main axis. So that's to represent phyllotaxis. That's why I use a parameter called phyllotaxis, which is like an angle, right? And then I generate a cylinder of certain dimensions, which are a function of what is stored inside the internode data type, right? So if you update the length field inside internode, then this will automatically update the size of the internode that is created in the scene. Okay. And then I give it a color, just like we did last time. So the important thing to see here is that this turtle operator, I could have put it in the rule. So in the rule that creates internode, I will show you later, I could have the RH there, or you can put it inside the feed method that is associated to the node. Maybe later I can show an example of how this will look like. Okay. No, that's the thing. So this RH does not exist in the graph. So if you look at the graph, and we'll later see the graph of this model, you're not going to see any turtle statement. It's all going to be just internode, node, leaf, bud, etc. And all the stuff related to geometry, including rotations, is inside the feed methods. So it will give you the same 3D mesh in the end, because the turtle is going to go through the same steps. But this is more procedural, so you're not storing the angles and so on. But then you need to store them somewhere else, right? So that's why in this case, because I assume that it's always going to rotate by the same angle, I store it in the graph level, and this information is stored in the internode itself.
Like if you want to have the phyllotaxis or the change during development or depending on the environment, does it matter?
No, it doesn't matter whether it's stored in a node or in a graph level variable. You can always update them. That's not a problem. The only thing that currently cannot be updated, and I think we actually tried in one project, are the rules. So once you create a graph with some rules, and the rules themselves you cannot change, right? But everything else you can always change in the graph. Yeah, so you have this left-hand side replaces something. That there are some specific cases where you might be able to, but most of the time you cannot change the rules once you create it. So anything that you want to modify, it needs to be stored somewhere as data, and then you can modify it. Yeah. So for the leaf, something similar in this case, because I already put the phyllotaxis in the internode. Here I just need to put the angle of insertion. So that's a different rotation, okay? And in this case, again, I store it in the graph level because it's a very simple model, right? And it's not even stochastic. Yeah. Rotate around the arm. So you have the head, the arm, and then the up vector. Yes, right? So you have to imagine that you have the turtles looking that way, and this is the right arm, and this is the shell.
So
Rotate over the. Okay.
so A is R.
Okay.
But apparently that's
Yeah, I forgot growing. And then it creates an ellipse, because very simple leaves, no petioles actually. And then I undo the rotation, right? Because then I want to continue later on producing more internodes in the main branch, okay? And okay, the reason why I have the bud node is actually to incorporate the branch angle. So the butt node has a very simple geometry, which is just this branch angle. But of course, in the rule, I could create the branch angle as a node itself. But my recommendation is try to do all the geometry, if possible, inside the fit methods and not in the graph. So keep the graphs as small as possible. Yeah.
It's like the set rotation command in Go. So you don't use a module to do rotation, but you just tell the geometrical object to rotate.
Okay.
I think that the problem was that if you would have two segments and you rotate this one, then this one wouldn't go with it.
Mm-hmm.
So that created a problem. It didn't stick somehow. I don't think we get the problem.
I don't know, maybe we will. We just need to try. It's not so difficult to break VPL, trust me. He is an expert at that already. Yeah, so we have the fit methods, creating the geometry, okay? And then we create our rules. So in the tutorials, I always have this organization, which is not necessarily the easiest to understand the model, but I think it makes sense for implementing the model. Then you start defining the types. Then the fit methods, so the geometry, then the rules, and then you create the graph, and then you do the simulation. So you put the functionality later. Of course, if you have a more complex FSPN, this could be just different files, right? You could have a file for all the data types like this, and that will be your module, and then you have another file where you have the fit methods, right? And another file when you put the rules and queries, etc. Right? So there's different ways of organizing. You just need to make sure that you execute the code in the right order. Because again, it's a dynamic language, so you have total control in which order the code is executed. So we have defined already the types that we're going to use in the graph. We have defined the fit methods to generate the geometry. So now I want to create one of the rules. So the first rule is the meristem rule, and this is for linear growth. Okay. So what I'm doing here is already showing the flexibility that you get in Julia because of the fact that this is procedural. So I'm first creating a function, phytomer. So this is, you can create simple functions in Julia just by writing the name, parenthesis, equal, and then this is the body of the function. So you don't always have to say function, something, blah, 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 end. These are like a one-line function. And here I'm actually writing a little graph. So remember that when we add nodes, we're creating a sequence like a subgraph, right? So this will be, you have a node, and then you have 3 children, the bud, the leaf, and the internode. And basically the internode is the insertion point, meaning that the graph continues in this way, right? So this is branching out, and this is sort of the main branch or the main path, right? So if you call this function, then it will basically execute this code, which will create a small little graph that represents a phytomer. And then you can use this inside the rule definition. Okay. So in here in the rule, we have a rule where every meristem in the tree is going to be replaced by phytomer followed by new meristem. Okay. So I could have put this in here. Okay. And in this case, it doesn't matter. But this is to illustrate that you can really compose everything in your model into smaller units, and you can reuse them.
So this is a new meristem on top.
Yes, it's a new object.
The old one.
Yes, it replaces the old one. It's considered to be like a totally new object. Of course, later we will see more advanced version where I think I keep track of the age. So then I need to make sure that the new meristem gets some information from the previous one. Okay.
Keeps the meristem and puts the new phytomer not above it, or replace it with phytomer, but put it.
Reuse the same object.
Yeah.
I don't recommend that. It might not always work because of because the objects keep track of their connections. That's a good thing, actually. What happens if you take notes? What happens if you reuse exactly the same node object without creating a new one? Yeah. Huh. I'm not sure if I tested this. It will be interesting. Yeah. So yeah, but it could be that it's very expensive to create this object. I mean, American, it doesn't matter, but it could be that you don't want to keep constantly creating object, but it might make the graph construction a bit more complicated. So I'm not sure if I thought about that. Yeah. So there's a way that you would say something like data mirror, something like this, and that will basically just dump all the data for the previous mirror stem. But yeah, computationally it's not efficient, but it's much safer for me. But we will test it, see what happens. So now I want to have the other rule, which is for the branches, right? And here I'm already adding a bit of functionality. So the buds are not always going to break because of apical dominance or lateral dominance or whatever mechanism, right? So I created a function that I'm going to use in the rule, which is going to determine whether a particular bud will break or not, right? So here we see now slightly more complicated. So for now, basically what I'm doing is the probability of bud break is proportional to the number of internodes up to the meristem in the main branch. So basically, if it's a bud node that is very far away from the apical meristem, then it has a much higher probability of breaking than if it's just next to it, right? And for now, I'm just using the number of internodes. Later, we will use actual distances. Yeah, that's what I'm going to explain again. So it's a function that takes a node from the graph, right? So bud, and we will use it later in the rule. Then what I'm going to do, so this is already some relational stuff. I'm going to extract the parent of that node, right? So a bud node, the parent of that node is a node itself, right? So we have a bud, and the parent of a bud is always the node of the main branch. So by saying parent on the object that represents the bud, we actually get access to that particular node. Not exactly. This is a movement in the graph. So a query, we saw queries, I think last time, or did we not see queries? I don't remember. But a query, it's something that you do at the graph level. Give me all the nodes of this particular type. This is establishing a relationship. So this is like the crazy stuff that you put on the left-hand side of growing rules, right? That is basically, yeah. But here you're going to do it in a procedural way. So you're going to say, okay, now I want to jump upstream, let's say, to get to this node, right? And then I use another function, this is all documented, of course, has descendant, which basically specified I want to look for a descendant. So this is a child or grandchild or grand-grandchild that meets this condition. So this is kind of like a query where you say, I want to find the descendant that is of type meristem. And this is going to tell me whether this node has a descendant of type meristem and how many steps it takes to get there. So what I'm doing here is I'm going to the parent node, which is the main branch, and then I'm walking down the branch until I hit the apical meristem, okay? And then I get the number of nodes in the graph that I have to traverse, right?
An apical meristem is a descendant of some bud sitting at the bottom of the stem.
No, you go to the parent of the bud. That is a node in the main branch, and then the apical meristem is at the center of that node. So this is like a weird cousin. I don't know. Okay, sorry. Botanical node. Botanical node. Botanical node. So this is an axillary bud in the next to a leaf, and this is the botanical node. Both of them are called capital N node, so this is a totally different word. Yeah, this is a lowercase node. Yeah. But I know that the parent of a bot must be a botanical node because in the rule, that's what it says. Yeah, because this is the type. So this is a constructor, so this construct an object of type node. This is a variable in a function. I can call this potato. I can say potato, but then I have to use potato here. Then I have to use potato here. Yeah. Ah, okay, sorry. Okay. There you go, Daddy. So,
That is fair.
yeah. Yeah. So here you're creating, I mean, how do you know it's because of how the language works? Here you're creating a variable. Here you're calling a function. But yeah, indeed, if I were to call it node,
But you call
there,
it because
yeah, but that's, yeah. Yes, exactly. We should come up with a different name for node. Yes. And internode. It's the thing between internode. Yeah. Sorry, Daddy. Yeah. Yes. So this is three types that node. So this node is defined in my module three types. Yes. And then virtual plan lab, but it's in a different module. It's virtual plan lab. It's different. Kind of call it graph node because it's an internal variable in virtual plan lab, but that is also called graph node. So sorry. But I understand. Maybe I would change the tutorials and call it botanical node or. There's no point. But is it clear how I'm moving through the graph? Yeah, because I don't have visualization here.
And the check.
If there won't be such a daddy, no. So the hazard sender assumes that daddy exists, because otherwise you don't have descendants. Now what can happen? So hazard sender is going to return true or false, and then as a second argument, it returns the number of steps
Right.
that it takes to reach the true node,
Yeah.
right?
So it gives you
So actually, I don't. Yeah, I've used check because I don't want to run. Actually, if check is false, then there's an error in the model because an internode should always have a descendant that is an apical meristem, unless you prune the tree, but there's no pruning here, right? So this is more like, yeah, this should succeed, but bugs exist. But the important thing here is the steps. It's counting all the nodes to get to the meristem in a straight line, right? So if botanical node, no, sorry, all the graph nodes until it hits the apical meristem. Yes. So it counts all the graph nodes until it gets to the apical meristem, and then the number of botanical nodes is half of that.
okay,
Yes. Yes. So then you see that I correct steps because it will count both botanical nodes and the internodes. Right? So then I know the number of botanical nodes, or the number of internodes is the same, until it gets to the apical meristem, and then very unrealistic model, I just assume that the probability is linear with respect to that, or 1. And here I'm using, this is what I was referring to, within a rule or a query, I can use graph data on my graph node to access the data that is stored at the graph level. Right, so bud break is a parameter of the plant, right, because I don't want to repeat it for every graph node. So I can access it directly. Yeah. Otherwise, you will need to have like a global variable or constant or something, right? And then I generate a true or false based on the probability, right? Because this function is going to determine whether this butt should break or not. So it needs to return true or false, right? So then I say, well, I generate a random number between 0 and 1. If it's smaller than prob, then it breaks. Okay. It is it's like runif in R. I mean, it's just a random number between 0 and 1.
Okay, so in this case, after four internodes,
Yeah, it will break. Yeah, because butt break is 0.25. No? Yeah, exactly. Yes, and of course, this could be a much more complicated rule. Right? But just to illustrate the idea, and then now we construct the second rule for our plant, which is the branching rule, right? So in this case, we're targeting the butts. And now, unlike in all the previous rules, I have this extra term, which is the LHS. So that is an extra filtering on the node, graph node, that I may replace. Because I don't want to replace all the butts. I want to replace only those that meet the breaking condition, right? And then if it happens, then I have a more typical right-hand side where I replace the butt by this new branch phytomer, basically. The butt node followed by internode, followed by meristem, and from that point onwards, this meristem is a new apical meristem for a branch. So then the other rule will apply.
If return,
Yeah.
after return, in this case, it's a true or false.
Yes. How do you know that this is true or false?
In growing,
Yeah. Yes. So Julia, you only define types when you only annotate the type of data when you create your own type. And that's for performance, actually. You don't have to, but for performance. Or when you define a method for a function. So when you do the feed function for internode, then you must say this is the method for an internode because it's a method, okay? And when you create a data type, I recommend that you annotate the type of each field. Otherwise, Julia will be slower, okay? But anywhere else, Julia will figure out the type itself. Is what it's called. It's based on type inference. But I mean, how would you know? I would just test it. That you say rand less than, I don't know, 0.25. Yeah, then you get a number. Yeah. You can do one thing. Actually, you can do one thing. Again, you don't have to, but you can add this. This is very advanced, Julia, but you can add the type of notation at the end of the function definition. And here you're signaling what I return must be a Boolean, or it needs to be coerced into a Boolean. If not, this is an error. So you can use this. And maybe give you some peace of mind. In my opinion, what tends to happen is that when you're writing your code, you want to be able to quickly change things, and you're prototyping your code. So you don't want all this type annotation. Basically, you want to have the experience of using Python or R, where you don't think about types, you only think about the science, the logic, right? And later on for performance and maybe for debugging, you might want to start annotating types in different places, but it always comes to a later stage. Yeah. So there's a thing called context, so you can actually return graph nodes in this function, which can then be used in the right-hand side, right? In Chrome, you can also do that. Like in your relational query, you can say, oh, I want to use the plan base, right? Normally then you give like a name in Chrome and then use that name on the other side. So you can also do that here, but then in that case, this function doesn't only return a Boolean, but it will return a Boolean and that additional graph node. So there will be an example where you might need to change the return type. Okay, and then we replaced. Yeah, that is.
Okay.
Yes, it's an extra condition. So I see it. I like to use the word filter. So with a rule, you first filter by type. So that's always at the beginning. Okay, and that's actually for performance reasons. And then the second step, you can optionally write a function that further refines your filter,
Yeah.
right? So the default for LHS is true, meaning whatever node of the type is going to be replaced. Yeah, you put exclamation mark. Well, no, I lie. If you want to do that, it will be something like this. It's always more complicated, like this. So you create a new function that denies this one, or you can change the code.
Yeah.
Probably easier. But yeah, in the end, it has to be a true or false, basically. Okay. So now we have the two rules to create new phytomers and to create the branches with this condition. Okay, and we have the geometry, so the leaves are ellipses, the internodes are cylinders, and we have the rotations for the turtles, the feed methods. So now the only thing that we're left to is the initial tree. So how do we start? So in this case, I have a little just internode plus meristem, of course no roots. So it's like a little hypocotyl and a little apical meristem. Okay. And now we assemble our graph like we've done in previous examples. So you define the axiom, that's the starting point of the graph. The rules, so now we have two rules. So we put them together in what they call a tuple. Well, in the algae we also have two rules, sorry, yeah. And now there's a third argument that we were not using before, which is data. And this is the data that you store at the graph level. Okay, so whatever you give it here, that is the data that we'll store in the graph. Okay. But this example, we only have one tree. In the next tutorial, I will basically make an array of trees and give them different parameters. Okay. So later we're going to do, so now I'm going to work in, so now once I have constructed the graphs, so the rules are there, the geometry is there, then I'd like to move on into the functionality, right? Because I want not just to apply the rules as development, but I also want the trees to grow and do something, right? And basically, if you follow all the tutorials, I don't know how far we will get today, in the end, like 95% of the code is the functionality, right? Because the basic, especially when you, in VPL, at least the basic code for the graphs is very small, usually. So because I want to do things with the internodes, basically I want them to grow, to elongate, I create a query, which I don't know if we covered in the previous tutorials. I forgot. Maybe not. Okay, so a query is like a rule. Internally works like a rule, except that you don't have a right-hand side. So in a rule, you have a data type, and then you have an optional function to filter. In the query, you have the same. You have a data type, and then you have an optional function to filter. And what it will return is an array with all the graph nodes that meet that requirement, right? So if I say query tree types internode, this will give me, if I now apply this query to a graph, it will give me all the internodes in a graph, right? And then I can modify the length directly, right? So rules are stored in the graph. Queries are independent from the graphs. Queries are associated only to the data type. Okay, so now if I want to elongate a tree, I create a function. You don't have to, this can be just part of your script. And I create a for loop, and what I do is apply to this graph this query. So tree here is assumed to be a graph implementing a tree, and then query is assumed to be a query object. Okay, so this will return an array of internodes, right? And then I can look over them, and then I'm updating the length of that internode. Okay. Apply is a function that I created. Yeah. It actually comes from R. We have the apply function in R. Yeah. Huh? Well, in R you have these apply functions where you iterate over an array or list or something. So it was my inspiration, but I made up this function, and it's always apply graph query. I don't know why it could be apply query graph, but it's what I came from. Yeah. And then you can modify anything stored in the graph. Okay. As long as you can actually modify the object. I think I talk about mutability. So you can create a struct that you cannot modify the contents, or you can create a struct when you can modify the contents. So you need to make sure if you want to modify the contents that you make it mutable, right? So I think in the definition of internode we should have, mutable struct. That means I want to be able to change the content after I create it. In a leaf, I don't have mutable. It means that once you create the leaf, you cannot update the length of the width. You could say I always make all my objects mutable. That would have slight performance impact, right? Performance obsessed, so my default is to not make them mutable, and then I make them mutable if I need to, but that's up to you, right? Yeah, so if it's just struct, then it's immutable, because that's, the philosophy in Julia is that it's what they call functional programming more than object-oriented programming. So in functional programming, usually data is immutable, and you are constantly creating new objects, right? And R actually works like that. Whereas, growing being based on Java, it's the opposite philosophy. The object-oriented programming means that you have these objects, and they have a long lifetime. You keep modifying things in the object, but you can also introduce a lot of bugs in your code by doing that, actually. You can do it both ways. So now I combine my function that implements growth in this very simple way. So there's just like a constant growth rate for each relative growth rate for each internode. Okay. And then the rewrite function, which, remember, this will apply the rules. Right? So now I have my daily time step that first applies the growth and then the rules. Or you could do it the way around. You could apply the rules and then apply the growth. Yeah, okay. So the exclamation mark does not have to be there. It doesn't have any meaning in the language. But the custom is that in Julia, when you have a function that modifies an input because it's mutable, then you give it an exclamation mark. Again, because people are always very afraid of changing things in place and this mutability thing. So whenever you see an exclamation mark function, that means that the first argument, usually only the first one, is being modified by the function. So this growth function does not return a new tree with the new characteristics, but it's modifying in place your tree object. Okay.
It feels a little bit overdoing it, that you have a function that's called growth,
Yeah.
but actually uses something called elongate. Because
Yes, totally.
Yeah.
Yeah.
So
I could.
why isn't
I could copy this here.
Yeah.
I think if you read the text, maybe it makes sense.
And one day step.
Yeah.
Then it makes sense. Grow.
Yeah.
And then I rewrite my rules. So I have development and growth. Normally we
You can imagine that this
That's why you
elongate
put it in
function, could be a much more complicated function that runs the ray tracer, calculates the simulates, etc., right? But yeah, of course. Yep.
But in growth, normally we have steps, like a day step, and then you say, okay, calculate life, and then calculate growth, and then develop. That's what these do.
Yeah.
Equal.
Yeah, maybe I should call it daily step. Yeah. Yeah. It is a daily step. You're right. You're totally right.
meaning then because
Yeah.
but here
Okay, so it's not even elongation. Okay. Okay, sure. Dynamic language, I can change things and rerun them. And now I have then my simulation function. So this is what runs the model, right? And still, it's a function that takes a tree as an input, okay? And then a query object, and then I run the number of steps. Okay.
Did you change 465 to data set now, or did that happen automatically because you changed it in 453?
Because I can have multiple cursors. So if you do Control D in Visual Code, it's search, and you can modify it, multiple instances at the same time. Yes. So now I have like the run, basically. This function is run, right? Without the initialization, right? So you take the tree and the query object as input, and look that here I'm doing this dip copy, because everything that happens afterwards is replacing the tree object in place. So when I'm now running simulation, imagine that you create one tree, you run the simulation, and then you say, oh, I want to run the simulation again because I modified my code. Now the tree object is no longer the initial tree, right? Because you've lost the initial tree state, right? That's the problem with immutability, that you lose information because you overwrite it, right? So what I do then is in this case, I create a copy of the initial tree, and then everything else is done in place. But again, this is Julia, so you can do it in any way. It's just what works for me. So that I always have the initial state separate from the actual evolution over time. Well, because then I can say, okay, I generate a new tree. I created a new tree before, so the tree was created somewhere here. Here I create the tree, right? And now let's imagine that I run my simulate function, but I realize that I make some mistake, and I want to fix my ray tracer. Then I can fix my ray tracer, and then I can run the simulate function again, because this tree is still unchanged. It's still the initial condition. Otherwise, I need to hunt for where I create the tree and run it again. And again, these are the kind of things that you encounter when you're using a dynamic language to develop a model and run simulations. In GROIMP, you always have to recompile the entire project. You change your code, you click and save, and it recompiles everything, and it runs all your code from scratch. This is like using R. You decide when you run what. But then you need to have certain practices, because otherwise it gets very frustrating, right? So you do need to change a little bit the mindset for these kind of little things. But some people don't work like that. I mean, some people would just change the code and then rerun it again in a new, from the beginning. You can also do that. And then it's a little bit more similar to what you do in GROIMP, where every single time you rerun all the code from scratch. Okay? So you have the options. So now we run a simulation of 2 days. And then here, this is similar to within Snowflake. I create the scene, and of course it doesn't work. Wait a second, new tree. Okay. I forgot to generate something, probably. I think I forgot to generate the feed function. As I keep talking. Yes. No. RGB not defined. Okay. I think I forgot to import something. Yeah. That's because, okay. Because I ran all the tutorials in order, so they're not independent. So I needed to import the RGB function. Import TLMaki.
I don't know. I know. I started from example 1 just now by running everything.
Yeah, and then it works because that's what I did before I uploaded it. Yeah, sorry, import color types colon RGB. So now I'm importing a specific function from the package color types. And so you can define the colors in VPL in any way you want, as long as it is supported by this package. So you have like different options there. And then it's
function again. So
yeah.
Simulate now, right?
Yeah. No, this is a function that I create a function simulate. Create function simulate. Okay. Yes, I can also call it that.
Immediately when it's something is already preset and then you gave it.
I understand. Okay, so now it's pre-compiling. This is Julia. Okay. And voila. We have a very beautiful tree with 2 leaves. Yeah?
The leaf.
Yeah. What do you mean?
The branch should be in the axle of the leaf.
What?
Yeah. Well, the leaf.
On the upper. Oh, he's the botanist. There you go. It looks beautiful. That's what matters. So we can do it again. So the original tree has no branches, but now I run twice because I said 2 steps, right? And then when I render it, it has generated 2 leaves. That makes sense because 2 steps. And well, actually this branch broke, but that was just by chance, actually, because it didn't have such a high probability. And then I run it 15 steps more, and you see that now I use new tree, which was returned by simulate. So this is the tree on the second day, at the end of the second day.
Yeah. 0 and this one starts at day 2.
Exactly. And now to the rendering, and then I get, and I mean, this stochastic, so it should look slightly different. So now I get something that looks a little bit nicer. It's still completely made up. This is not a real tree, but
Right. I mean,
yeah.
the bare essence of tree.
Bare essence of trees, yeah. Yeah, so this is because of the lighting in the 3D rendering, which you can change, but I never bothered to look into that. Yeah, but that's again by chance. Because it should be all exactly green, but there is some lighting, and this is causing the colors. Huh? Yeah, you can make changes to the figure yeah. So when you do render, you can actually store these in an object, and then there's a package called Maki, which is managing all of this, and then you can change the cameras, you can change the lighting, you can do animations, you can do many things. Okay. I thought you were stating. Yeah. Yeah. They're all exactly the same color here. Wait a second. Yeah.
code that gives different shapes.
So this should all have the same. I've never tried to change that. Yeah. Yeah, I think if you give it just an ambient light, then it will not have any shading or anything, because then all the leaves receive the same lighting. Okay, but I will look into that. Mackie change. Yes. I think the defaults for the rendering package change, because I don't recall. I've never touched the lighting. It looked very ugly. Okay. Okay. So we will look into that. Huh? I will think about it. Yes. Yes. Yes.
Looks better.
Okay. Okay, so that was E3. If you want, we can take a break now, a short break, and then we go into a forest, which should be relatively easy. Pause, so I don't have to do so much editing. You were pause. Now you're not pause. I hope it's recording. Yes. Anyway. Okay, so let's continue with the forest, which is basically an extension of the previous model. Actually, in terms of functionality, it's the same. But what I want to illustrate now is this point of having a separate graph per plant, and also changing parameters for different plants, right? I'm looking a little bit into variability. So I'm going to fix the code by adding the statements that I will need, just so that is independent of the previous tutorial. So we use again Virtual Plant Lab, the color types, GL Mackie, so this is the graphical backend. And then going to be use a couple of more Julia packages, distributions and plots, and that's just to do like a little bit of data visualization. So that's like not strictly speaking FSPM, but it's part of the workflow. So tree types is exactly the same, okay? Because the trees are exactly the same. Sorry? Not while I'm running it. Okay, yes. Oh. Okay, so the individual trees are the same. So we have the same module, tree types, and we have the same feed methods. We have the same rules. So I just copy paste this from the previous tutorial. So I'm just running the code again, but it's exactly the same thing. Okay. So now I have a slightly different way of creating a tree, because now I'm going to generate trees on a grid, right? And in this case, I am using some turtle operations that are added to the axiom. So before creating the initial state of the tree, the internal plus meristem, I use T, which is to translate. That basically moves the turtle to a specific point in space, and then I do the random initial orientation of the plant, right? Which is how we often incorporate stochasticity in our plants. And then the rest is the same, except that when I create the graph, not only am I going to have a different origin and initial orientation, and that's part of the axiom, but I'm also going to have a different growth parameter and bad break per tree. Right, so this is where having defaults works very nice. All the parameters are going to be the same for all the trees except growth and bad break, which are going to change. And then I wrap this into a function, create tree, which takes as input the specific things that are changing per plant. So you give it the origin of a plant, the initial orientation, and the values for bud break and orientation, and then it creates a tree with those settings.
Growth and the bud break that you use as an argument there for create tree.
Yeah.
Second growth, the second bud break in those lines you highlight.
Yeah, so growth, the first growth and the first bud break are the names in tree params.
Yeah.
And the second growth and second bud break are the variables that you're given as input. Yeah. For people who use R, this is very clear. Yeah. Or used to this kind of program.
I mean, it looks strange, right? Growth equals growth.
Yes, I know. But it's equal is never equal in program. It's assignment. You assign growth to growth. Yeah. Yes. I'm getting a lot of feedback, yes, about the Vudivit tutorial. Thanks. You can call it my bud break, my growth. That usually helps. Yeah. Okay, so now I'm going to be creating the trees using this function. But then here I copy paste also the functionality from before. So this is again copy paste from the previous tutorial, from the tree tutorial. So the elongate, the daily step function. Okay. The simulate function and the query object. Okay. So what I do now is that I'm going to create the values for origin, orientation, the growth parameter, and the bud break parameter. Okay. And I just went for a 10 by 10 grid. So 10 trees by 10 trees with just a fixed distance of 2 meters within rows and across rows, right? So here, this is just a bit of Julia code. It's what I call a comprehension. So it's a way of doing for loops that is a little bit more compact, but you don't have to do it like this, okay? Any way in which you can create a matrix in this case would work. But basically what origins is a matrix where each element of the matrix is the coordinates of the tree. So this is 1, 1, 0. 0 is the height, of course. 1, 3, 1, 5, 1, 7, 1, 13. So we're moving in one orientation, and then in the other dimension of the matrix, we're moving in a different dimension. Okay. So I like it to do it like this because then you're almost matching the actual arrangement in the field. You know, you could say that these are rows, and this is within a row or whatever. Okay. So we do the same for orientation. So in this case, I'm generating a random number uniformly distributed between 0 and 360 degrees. In a VPL, all the functions that take angles that you will be interacting with are in degrees, hexadecimal degrees. Okay. Internally, things are in radians because that's the correct way of doing it for the math. But I make sure, and if not, it is a bug, that you only have to think in terms of degrees. Yeah. Because radians are, is not what we normally do. So I also create a matrix with the initial orientations. So this is angles with respect to the north, right? And this matches the matrix with the origins, right? Now I'm generating some random numbers from a log normal distribution. And then I'm going to make a histogram just to, just to visualize it. Okay. So again, this is from the distributions package, and the histogram is from the plots package. So every tree gets its own growth parameter, this relative growth parameter. Yeah. Think of genetics or nutrients or something. And it gets its bud break parameter, so this 0.25. So now each tree gets a slightly different coefficient for the bud break, right? Of course, in a real scenario, this would be distributions that you determine from measurements, right? And then you just parameterize those distributions and generate from them. But the nice thing is that within Julia, you can do all of this work and also do the visualization interactively, right? So now you can call the create function on all of this data, right? And if you just do create tree on these values, it will generate a matrix of trees. But you don't see it because I don't print it. But technically, this is a matrix where each element is a tree object. But then I explain it somewhere here that you actually need to flatten this because VPL wants everything to be in an array. Because yeah. So now we have the forest. So the forest is basically just an array of trees. So if I say forest 1, it gives me the first tree. Forest 2 gives me the second tree. Forest 3. Which is always printing the same thing because I don't want to print the whole graph. You don't need to know. Yeah. Yeah, so what you can do is, yes, so I mean you can do it like this, but I know that later, basically so at the moment when you create the 3D scenes, it wants a flattened array of trees. I need to, but that's a feature that I need to add to VPL, that you can also give it matrices of trees, right? But that's something I need to add. So if you do it like this and you say forest 1, 1, that will be the first tree, right? And this corresponds to origins 1, 1. Which is the 1, 1 coordinate, right? So you can keep it like this, but VPL is not fully compatible with this data structure yet. I will eventually make it. Yeah. So I want to support any kind of arrays so that you can organize your graphs in any way that you want. Actually, I want to make it as generic as possible. Anything that kind of behaves like an array, I will do the flattening internally. You can also store the location tree params, yeah. But that I would do that if it's not part of the axiom, or just to retrieve it afterwards. Yeah, sure. That's also possible.
A 3D array sensor.
Yeah. Yes. Yeah, so I think basically all n-dimensional arrays are part of, they inherit from the same type. So I can write genetic code, but there's some steps that I did not, I didn't prepare it basically yet, but yes. So if I flatten it for now, then I can already do the rendering. Looks very tiny. Zoom in. Here you can see all the little initial plants. Okay. And remember, by default, you will get a grid in the figure with axes, but you can turn that off. But at least when debugging, I find it useful because you can also check what the coordinates are. So you get all the little plants. Look very similar because the only thing that changes is the orientation. Yeah, because I already, yes, you're right. I already did the simulation. Wait. Yes, I already simulated 2 days. Sorry, you're right. Let me rerun this again because I lost track of what I was doing. Yes. So I don't need a back here. That's the thing. Yes, I created the trees and then, sorry, I did the simulation for each tree using, again, this comprehension, which is just a way of doing a for loop in a more competent way. So for every tree in the forest, run this code. Yes. So this is something they copy as far as I know from Python, array comprehension. And now you can do the same thing, but now you call it 15 steps, just like we did before. And now we get a forest after 15 steps, right? And you can see these giants because they get a very high growth parameter, and then the tiny little guys over here. So the width scales with the length in this model, and you can see that these are really cylinders, so you get this kind of Yes, exactly. Yeah. So that's how easy you go from a single plant to a field of plants, basically. You just create a graph per plant, and then you vary per plant whatever you want to vary. And it just means that now you are always working with an array of graph objects rather than a single graph, right? So you basically have to do a bunch of for loops. Okay. And whenever you want to render them, or later when you want to use the ray tracer, then you apply the scene object, the scene function on that array of graphs, and then it creates a 3D scene. Okay. So everything that happens within a graph is independent from other graphs because these are contained objects, so they have their own data. They have their own copies of the rules, right? So this is all contained. So you can run everything in parallel, right? So in this case, I share two examples of how to run in parallel. So in this case, I'm basically running each plant in parallel, okay? And that basically means when you run in parallel, I mean, you need to look at Julia, how to do it, but basically you use this add threads macro, and then you write a for loop. And this means that this for loop runs in parallel. Yeah? In series. Yeah, so this array comprehension is running in series, but this is equivalent to basically this code I'm writing here. So this is like the fully expanded for loop. And you create a new array of trees. So new forest is a new array of trees, and then you update those trees using the simulate function, but then you do it in parallel. So this will be one way. In practice, you normally don't do this. Well, this is what happens. Basically, it just already run. In practice, you will not do this because normally every daily step, you want to use all the graphs to create a scene. Like if you're running the ray trace, if you're simulating competition between plants, at some point the plants need to interact with each other, right? So your code cannot be 100% parallel for different plants, right? Then that means then that the plants are not interacting with each other or with the environment. Yeah. So an alternative way is that you step over time in a linear way, right? But then within the daily step, whatever you can run in parallel, you can do it, right? So you could imagine that first you construct the scene, run the ray tracer, you compute the simulates per plant, but from that point onwards, everything else can run in parallel because it's internal functions of the plant. So only the part where there's interactions between the plants, that's the part that you cannot run in parallel. Yeah, of course, the ray tracer itself will run in parallel. So you sort of have parallel execution, then it converges to create this 3D scene and all the ray tracing stuff. And then the ray tracer again uses all the threads, right? And then you go on in parallel again with plants. So the idea is that as much of the code as possible can be run in parallel. And actually, technically speaking, the scene itself can be run in parallel too. But yeah, usually that's not much of an advantage. Yeah, so this is the whole simulation with the second approach, where it's sequential in time, but parallel within daily time step. Okay. And this is actually one of the main advantages of having a separate graph per plant, because then it's really trivial. I mean, there was a few things that I needed to ensure for this to work, but yeah, you gain a lot of computational power by doing this, right? And this is more important than any improvement we make on individual graphs. Like what we were discussing before about how efficient is a graph implementation. It also allows you to keep the graph small, which will also speed up any rule or query that you run on individual graphs, because you are always dealing with smaller graphs. So you have smaller graphs that can be processed in parallel. What does that mean? Communicate? Yeah.
You have calculated that by visualizing the exact location in 3D cloud.
Yeah.
And that's another part. But if you don't have the graphs linked, okay, that's okay. But then
Touching
also
it,
didn't,
it's a geometrical.
yeah, we didn't do
Yeah. So you generate the scene, and then I will need to implement some kind of collision detection.
Where you would have mycorrhizal fungi.
Yeah.
So like
And
a network of
communicate from
threads where you have transport between plants. Then they need to be in the same graph.
Well, I don't know. I mean, you can basically program the transport yourself. So you can say, okay, the individual graphs communicate with the hi-fi, which is an object that you owe, and then the hi-fi communicates with the individual graphs. But you have to program the medium, because that, to me, that sounds like a different biotic environment, basically, right? Biological environment. So yeah, basically the abstraction that I have is that plants are agents, individuals, and the physiology is internal, right? And everything that has to do with environment, indeed, you need then to bring all the plants together, hey? And then normally you create a 3D scene, and then you run some environmental module, which is light transport or water uptake or microclimate or whatever, right? And then you go back to individual graphs. Yeah. And at the moment for the ray tracer, so these connections can exist. So the ray tracer, which I'm not sure if today we will have time to go into, modify the original graphs directly. So you actually create a connection between the graph nodes that contain material properties and the 3D scene. So when I create the 3D scene, I keep track of which optical properties correspond to which triangles. So then I can store the radiation stored in those optical properties, right? So the power, right? So you can get information back to the individual graphs. Yeah. That's the idea. Right. And what I show here is an aspect that we didn't cover so far, which is, okay, so far we create the scenes from graphs using this feed method, but you may have, or well, at least you have a soil, right? And you might want to include the soil for visualization or for the ray tracer, but you may also have other structures, like in a potato crop, you want to, take into account the ridges, or in a greenhouse, you want to have some structure, right? So you can also create geometry objects manually, right? They're not represented by a graph. So you can create geometry without a graph and you can add it to a scene, right? So in this case, I create a rectangular tile of 21 by 21 meters, okay? And I'm not sure if it's fully documented, but basically whenever you create an object, it has like a default orientation and default location, and then you need to rotate it and move it, okay, to put it in the right place. So in this case, we create this rectangular tile, we rotate it 90 degrees because originally it's vertically, I want to put it horizontal, okay? And then I move it to the center of my field, okay? So basically what I'm creating is a rectangle that is going to represent the soil, okay? The soil surface, yes. I created my scene from the graphs, so now I can add to my scene that soil. So mesh is the 3D geometry that you generated, and you can specify the color, okay? And then I can render that new scene, and now you can see the soil. In this case, I also remove the axis, okay? And of course, this is nice for visualization, but also for ray tracing, you want to have the soil, of course, for soil reflectance, okay? Yeah, so you can do this, and of course, if it's more complicated geometry, you can generate it ahead of time and store it and just import it into your project and you add it. It is possible to export the meshes and to import the meshes. So if you have a 3D mesh from some external software, you can import it and you can use it inside a graph. So there is a method to just, use an existing mesh, or you can also add it to a scene. Okay, so that is possible. Yeah.
So what if you want the soil to be, you want to store data and extract data from your soil files? Then you have to.
No, not necessarily. I mean, in that case, I would, if you want to, for example, store the light absorbed, then I would recommend maybe do a graph that just has an axiom, so it doesn't have any rules, and you just follow the normal workflow. But I mean, maybe I will add a tutorial on how to do like a manual soil with ray tracer, because you just need to define the material object. I may actually have it. I think I may have it. Maybe not as a tutorial, but as a test. You can create your own material object. So this is where the light absorber will store, and you just give it when you add to the scene. So you don't need a graph at all, actually. You can create a whole scene with colors and with these material properties without ever using a graph. The graph is just there when you want to generate it for a plant, because you want to rely on these turtle algorithms, right? Yes, you could do that. Although then I would wonder, in the previous 35 days, the plants were like floating in space. I mean, or maybe they were not driven by light. Maybe it was like an empirical model.
The light model,
Mm-hmm.
but if you want to do light extinction or ground cover,
Mm-hmm.
or you want to see how much light actually reaches the soil, then
Yeah.
often I want to know what is the light absorbed.
Yeah, so you can do it. And the thing is that you can do it with a graph and just a graph for the soil, or you can just create an object that represents the soil file, and you, without a graph, you can do it also. But and get data from it. And yes, and I think in the later on I may have a tutorial where I do that. I don't remember right now how I did it, but that is possible. Yeah. So in fact, the whole, let me explain it this way. The Julia package, so VPL has multiple Julia packages internal. The Julia package that creates the scene does not depend on the Julia package that implements the graphs. It's completely independent. It's only the turtle that connects the graph and the geometry, right? And the ray tracer depends on the geometry package. It doesn't depend on anything else. Yeah.
Geometry, then
Yeah, but I will show you later. I'm not covering the ray tracer, but there will be an argument called material, and then I give it some object here, and then that object will store the power absorbed by the soil. And for the graphs, I will use in the feed method. I also have a material. Okay. And here I showed you an example of how to export a scene. So I'm not exporting an animation, but it's just a snapshot. Okay. So you can, well, I create a function to help you calculate the resolution, because people are always confused about this. So you can give it the dimensions of the figures and the DPI, so the dots per inches, and then I compute the pixels for you, how many pixels your figure should have. So you can do this, and then you can do the rendering, you give it the resolution, and you store it in a variable. Okay, so this creates this, okay, just like before. But now I have a reference to this figure in this variable called output. So you can actually interactively choose which angle you want and which zoom you want, okay? Like this, for example. And then you go back here and then you run export scene. Okay. So this is still there, still working, but now we've taken a snapshot. So we go to the folder, we should have nice trees, and it's taking a snapshot of what you were seeing. Right? And you can take multiple snapshots. You can keep running this. Okay. Res, yeah, it's a tuple with 2 values. So are the pixels. Yeah, you can enter like a HD or 4K or something like that. You can enter. Yeah. Because I wanted very high resolution. Yeah. But yeah, you can give like the numbers for HD, 4K, 8K, whatever. But I use this for people who indeed want. I mean, this is 16 by 16 centimeters with 1000 dpi. For publication, usually they ask 300 dpi, right? So that will already reduce the number of pixels, right? But it's just to help people come up with a number. Yeah. Okay, so that was it for the forest. So here, basically, we learn how to combine multiple plans, how to add some geometry, and how to export screenshots. If you want, we can have a break now, and then we move into the growth-driven forest, where there's going to be more functionality. So shall we have a 5 minutes break? All right.
Correct.
Yes.
For a tree.
Yeah.
I was wondering, can't we have a field parent for the field?
Yeah. And actually, you could create an object for the field that stores the graphs inside of it and other information.
Yeah, like the distance and the number of trees.
Yeah, and then when you create that object, it creates the plants.
Yeah.
That's what I was referring to. I will have a function or an object.
That's what you mean.
And that function takes as input the settings for the simulation, and then it creates the field, and then you can simulate the field. Yeah.
Not convinced? No,
Yes.
I'm convinced.
I mean, eventually, some of the reference models will be implemented like that, because there will be a package that implements a model, and then when you want to run a simulation, you're just calling functions in the package, and it creates everything. And I think that is much better and so it's safer than having 10 scripts with information all over the place that you need to change manually. Also easier to document, because you just document the function that runs the simulation, and those are the inputs of the model. And you could call that from R, for example. So for people who don't want to learn Julia, but they want to run simulations, you could actually have an interface from R. You can create like a graphical interface that runs, right? So if you have a function that takes the inputs and does everything, then it becomes so much more powerful. You can run simulations in parallel very easily, these kind of things. But I would do it step by step.
Yeah, just now I was trying to change the number of trees. So.
Yeah.
And it started complaining.
Yeah. So the first step will be to parameterize it, and then iteratively you slowly start to encapsulate it into more and more functions. Yeah. So never try to do it from the beginning in a very complex way, because then it becomes unmanageable. And that's the nice thing about dynamic language, that you probably can do all of this without restarting Julia, right? You're just in the same session all the time. Okay, so in this tutorial, we're still not looking at the ray tracer. I think that comes later. But basically, I add a little bit more functionality. Okay. So I'm addressing issues like, how do you update the dimensions based on amount of simulates? And also I'm adding some carbon allocation. So we're not really, I'm not sure if we are going to learn any new functionalities, but let's go through it anyways. Okay. So essentially the same type, the same three types module, difference that now the meristem has an H. Okay, so I'm going to add, I guess I'm adding a plasticron. Okay. The internode has an H, it has a biomass that's going to be updated over time, and then it has the dimensions, and it also has a sync strength, which I implement as a distribution, but I really use as a function. So it's basically something that decays with H. Okay. And that I store in the internode, although this could also be stored somewhere else, right? Because it's not really going to change per internode. The parameters are the same, basically. But yeah, here I did it at the organ level. But this will be like a photosynthesis model. No. So exponential is an exponential distribution. So think of an exponential function where the x-axis is time. So it has. Yeah. No, it doesn't depend on the environment. It's the potential sync strength of an organ, which is based on its age. Okay. And for leaves, we have something similar. Okay. And now we have a tree params that is a little bit more complicated. So we have the biomass of the whole tree, because I'm going to do a relative sync strength model. So I first collect all the growth. Well, in this case, it's a bit complicated because I simulate total growth and then I distribute it according to the sync strength. So it's not exactly, well, yeah, like that. Yeah. And then we have similar parameters from before, the relative growth rate. So that was what I call growth before. And then I have some parameters related to biomass. So the initial biomass of an internode, initial biomass of a leaf, the specific internode weight, specific leaf weight, and some shape parameters, right? So essentially it's the same models before, it's that now we have a growth, we have carbon allocations, so the assimilates, let's say, are still being produced in a very simple way, so there's no light interception yet, but at least now we have this relative sync strength model to decide which organs grow more or less, okay? And we're also adding age or thermal time to drive development, so we don't have every day the meristem produces a new phytomer, right? Or the brake will break as soon as there's no apical dominance. Okay, so it's starting to look more like a realistic model. Here's the ankles. Okay. So you see that now we're starting to add quite a bit more data, but the overall structure is still the same. Right? And as always, yeah, so here, for example, yeah, I said sync and it's stored in the organ level, but in this case, there's no point because each organ actually has the same model for sync strength. But okay. You could imagine that different organs have different sync strengths for whatever reason, right? Like maybe the tillers, they have a different sync strength in the main branch of them. Right? Then these are the same as before, because we're going to use the same information. So the geometry is generated in the same way. Okay, so now we have a slightly more complicated meristem rule. Okay. Basically because we're going to have a extra condition, right? And basically what I'm doing in this line of code is I'm comparing the age of the meristem. So data allows me to access the data stored in the graph node. Graph data allows me to access the data stored in the graph that the graph node belongs to. Right? So data can be stored inside the graph node or the graph that it belongs to. So you can access the first one with data, the second one with graph data. So then I compare the age of a meristem with the plasticron that the plan has, and then the modulus operator basically captures modulo equals 0 means is it a multiple of, right? Like if the plasticron is 15 and let's say the age is 10, then it hasn't completed one plasticron. The moment that it becomes 15, then the modulus equals 0, right? Of course, this wouldn't work with like continuous thermal time, right? Because you're jumping over, right? But this is still based on days, so, right? But the basic idea here is that you will use the information in the organ, in this case age, to determine when the new phytomer is produced.
And the
Yes, each time that all the meristems in a tree are going to be tested with this function, and only those meristems when this is true, right? Those will then generate a new phytomer. Because I first select the graph nodes that are of type meristem. You always filter by the data type first, and then you know that you're always going to be working with meristem. Yes. So it's a variable name.
rule is
Meristem. Yeah. If this was leaf, then this code would not run because a leaf doesn't have an age. Yeah, or maybe it does. I don't know. Yeah. Okay, but it will be weird. And then this was actually the same code as before, the phytomer. In this case, I didn't put it as an independent function. I put it in the rule, but then you can see that the rule becomes a bit harder to read. That's why I think that sometimes it's nicer to put things separately. But the difference here is that now I am initializing the leaf and the internode to a specific biomass and length and width, which you get as input. Sorry. And again, belief and vint can be whatever you want, right? So this is a way of parameterizing the initial conditions of the leaf and the internode. And this could be stored in the graph. So belief and vint could be stored in the graph, or it can be something external to the graph, right? So again, I'm just showing you different ways in which you could do it. If you're never going to change the initial biomass, the initial length of an organ, if they are, let's say, constant, then it makes sense to have them outside. Only store in the graph the things that are somehow going to change across plants or over time, right? And then we have slightly different probability of bad break. So this is getting a little bit more complicated, but it's similar to what we had before. Before we were counting the number of internodes. Okay. Now I do something similar. So we go to daddy. That's the same as before. But now I strike the first internode. Okay. And how I do that is that I get the children of daddy. Okay. So I get all the children, and then I say, give me the children that is of type internode. This is what it means. And so of all the children that daddy has, give me the one that is of type internode, and if there's more than one, give me the first one. But yeah, it's only going to be one. Okay. So this is Julia code. So the filter is a Julia code. You could do it in different ways. You could first store the children, then loop through them, and get the one that is of the right type. So again, this is just Julia code. You can decide how to write it. Okay. Then I extract the data stored in the child, and from there I'm going to get the length. And basically what I'm doing here is I'm repeating the same procedure where every time I look at the child of, so I get an internode, then I look at the node afterwards, then I go to the next internode, and I'm updating the length. So this is the key line. As long as I have a child that is of type internode, then I update this distance with the length stored in the child. Okay. If we encounter internode, sort the length above and move to the next node. If we encounter a node, extract the next internode. Right? So you're looping all the time until you get a meristem. So when you get a meristem, then this while loop breaks. So this is running as long as you don't hit a meristem. And if it's not meristem, then it's either internode and you update the distance, or it's a node, and then you move further.
Where you use data underscore type.
Yeah, because depending where you're in the code, the data child can be, okay, so here you are in a particular node, right? And I call it data child. Here, I could use, yeah, I think you're right. I think you could, I think because I'm reusing it, because otherwise I need to call data child here again, data child here again. So because I'm using data child multiple times, I just save it in a variable. But you don't have to. You could replace all the data underscore child with this function. Okay? And maybe that makes it easier to read. I don't know. Yeah. And basically you update here when you move to the next one. Yeah. So yeah, it's a little bit complicated. I don't expect people to read it or to understand it fully. But the gist of it is that I'm now creating a very specific, I don't even know how to call it. It's not a relational rule, but it's like an algorithm that is computing a quantity that depends on the relationship between organs, but also on the data stored in those organs, right? And what helps is that you sort of keep in your head a visualization of the graph and figure out where you are at each point. Yeah. Yeah, you need to start somewhere. Because it's a graph structure, so it's recursive. So actually, first you're dealing with the child of daddy. But later you're going to deal with the child of daddy, so the grandchild. And then the great-grandchild, and so on, right? But this is what this for loop is doing. It's repeating the same thing, and so again, we're getting children, child, one, etc. Okay. Basically, this filter is exactly the same as this one, by the way. It's the same code. But I need to start somewhere. So the first iteration, I do it outside of the loop, and then I keep running the loop until I hit the meristem. This code could be written much better, okay? So it's not necessarily the clearest code, but the idea, yeah. Yeah.
And from that, you're calculating the bus width.
Yes. So it's the distance to the meristem. Yeah.
Gives a distance from any bud to the meristem.
And then the probability. Yeah. 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 Indeed. And I could also do it in the way you say. Like I could also just get all the descendants that are internodes and then get the length and add them up. So there's many different ways in which you could do it, right? And this is, let's say, where your Julia skills come in, right? The different ways in which you can achieve the same goal. Because here, what I give you are just the tools to get the children and the parents of the graph nodes, right? Essentially, that's what you do, or to check if a particular descendant or ancestor exists, right? That's what VPL offers. Allows you to navigate to the graph, but then you can come up with any algorithm you can think of, right? So in this case, indeed, we have this relatively complicated left-hand side rule that is based on accumulating properties of something. I'm sure that you could do this in GrowImp. I don't know how, but the thing is that this is procedural, and I didn't write this function in one go. the first time I wrote it, it didn't work, right? But because it's a function, you can debug it. You can print things from within it, right? You can work with it because it's just code, right? That's what I like about having all the rules implemented as functions. And the rest is the same. So now we have a more realistic, or slightly more realistic breakpoint probability rule. Okay. And then I have some functions to compute from the biomass the dimensions of the leaves on the internode, right? So this is a bit more specific, but this is often what we need in an FSPN because we usually do growth based on carbon or simulates, and then we compute the structure, the geometry based on shapes and things like that, right? So this is basically given the biomass of a leaf and assuming that it's a ellipse and it has a certain width to length ratio, how you will calculate the length of the leaf, right? That's what this function does. And this is something similar for the internode. Okay. So these are external functions. You give it any, in this case, you give it biomass and you give it variables. So these vars is, yeah, just packing different, actually, you would use the 3 params for this because this is stored in 3 params. Yeah. No. So in Julia, objects do not own functions.
Yeah.
Objects just contain data, and functions are doing things on objects, right? And you can have different methods of the same function for different data types, right? Or in this case, leaf themes only has one method, right? Which is to work with leaves. So you don't have to specify. But you could imagine that you have like an abstract version of this. This could be abstracted. Given a particular type of geometry, if you can be the biomass and the specific weight, then you could apply this function to internode, to leaves, to. And then here I was playing with the sync strength, so I implemented a function to calculate the sync strength of leaves and to calculate sync strength of internodes. And basically, I'm just using, yeah, it's a bit complicated, I realize. But the idea is that you have a leaf object and then some additional variables that are stored at the plant level, and then it computes that beta distribution or exponential distribution that I described, right? And because I'm in Julia, I can actually plot this and I can play around with the parameters here. So this is the visualization of the particular function, right? And then you can tune this and just plot it until you get something that makes sense. So this is for the internodes. And so what I'm doing here, PDF leaf sync, this is from the distribution package. So sync is a distribution object that is stored in the leaf. Okay, it describes the distribution with some parameters, and when you call PDF on it, it generates the density function. So I'm using the shape of density function as a sync strength. Right, so here I'm plotting both, so internodes and leaves. So in this model, the internodes demand much more than leaves, right? And you see that in the internodes, it decays exponentially. In the leaves, it has a bump, and then it goes down, right? But again, this could be any function that you choose. Okay. Then here I define the queries. So this is a function to give me the leaves of a tree and a function to give me the internodes of a tree. And this is the same as before. So I apply to the graph query objects. Okay. So you can see that basically, again, the problem with the tutorials is that I'm building all the pieces first and then you make the puzzle, right? And then it's a bit harder to see the overview, okay? But this is not necessarily how you develop it, right? The way you develop it, maybe you start with a simpler model and then you start adding complexity in between. Okay. But effectively, most of the time, you're going to be defining functions that do different things on different inputs. Okay. So I have a function that updates the age of all the organs. So it's okay. So you give it the organs that you must have obtained somewhere else, right? And then it just increase the age by 1. And then I have the daily step function. No, this might actually be a growth function because here there's only allocation, there's only biomass. So this is a true growth function that gets a tree and it gets the leaves and internodes, and then it computes the growth of the tree, basically biomass times a relative growth rate. Yes, so you can have Unicode in Julia. You can have emojis, you can have hearts as variable names. That's all fine. Yeah. Yeah, so basically you need to know how it's called. So you type this, I never know how to call this, symbols, and the delta, and you press, wait, because this is a markdown environment. This works better in either in a console or in a script. So delta, this is the lowercase delta. And then I don't remember for the emojis, but they have code somewhere. There's like a name, and then you press tab, it will replace it by the code, right? And this works, no problem. It's always a bit more difficult on Windows. In VS Code, they have plugins, as long as you're working on a Julia script, so you can do it. But if your code is going to be called by another program, like R, Python, or whatever, then don't use Unicode because they don't understand it. Right? I once wrote an entire model with Unicode with a lot of Greek letters, and then the R package that calls a model, and then I have to rewrite it because R doesn't understand all the Unicode. So yes, the delta B. Yeah. Maybe. So indeed, I calculate the delta B, the delta biomass, and then I update the biomass in the tree, but then I also update the total zinc strength first. So I calculate total zinc strength from internodes and leaves, and then I calculate the relative zinc strength for every organ times the biomass, and that's how much that organ grows, right? So this is basically describing a very simple growth model, so relative growth rate, but then you have a global pool, and then you have the relative zinc strength, right? And here what we're using, so all leaves and all internodes, is the array with all the leaves and all the internodes that I must have collected somewhere else, right? And then I can access all the information inside those nodes and update it, right? So the idea here is that you run the query once per day. So, at the beginning of the day or whatever, you get all the leaves, you get all the internodes, and then you call different functions that modified those leaves and those internodes. So you don't have to rerun the queries multiple times.
All the leads.
Yeah. No, you could because now, yeah, I don't have it here. I can show you later, but yeah, you can access all the data. You basically get an array of the objects. So you can now say, I want a subset of these where that age equals as larger than something. Yeah, you can filter again. Yeah.
Can I have any remaining biomass here? Right?
No.
Because you didn't.
Yes. No reserves. No. And it's yeah, it's the assumption is that it's always source limited. That the total zinc strength is always much higher than the source, which is not necessarily the case, of course. Um,
Something just confused without like giving any specific.
Like a void function.
yeah. So you don't have to do it. Like if I don't type return nothing, it will just return nothing. So basically what happens is that the code in the function is run in the order. And whatever is created at the end, it will be returned, right? Now a for loop doesn't return anything because a for loop is just updating this int biomass. So by default, this will return nothing. But yeah, I like to add it just to emphasize that this function doesn't return anything because all the changes are happening
In the product.
in the leaves and the internodes and the tree that you gave me as input. So it's modifying the inputs, right? That's why it gets exclamation mark. And this is basically the philosophy that I have for all the models that I've built so far. You have your trees, you have your arrays of organs, and then you apply functions on them that modify their content, right? And then at the end, you can also then rewrite the graphs to create new organs. So now here we use the leaf dimension functions that we defined before to update the dimensions of the leaves and the internodes. And now we have the daily step function that puts everything together. So now it's when it starts to make sense, right? So in a daily step, we get a forest, then we loop over the forest in parallel, okay, so that we get individual trees. Then we retrieve the leaves, the internodes, and the meristems using queries, okay. No. So I'm still defining the model itself, and then at the end, I do the simulation, and that means the initial state. Yeah. So you could imagine that this will be like in a separate file that defines the model, right? But it's daily steps, so I loop over the forest, I extract with queries all the organs, and then I apply the function that updates the age. I apply the function that updates the biomass, and this will call the ray tracer in a more complicated model, right? And then I need the tvars. So again, I store it because I use it multiple times. But basically, these update the dimensions from the biomass, and then I apply development, right? So this is, before we just had elongate. Now we have actual growth, and then age, growth, and updating the dimensions, right? So it's starting to look like a more realistic plant growth model. Yep. Yeah.
With the things.
Yeah. This one.
So you do this for all leaves, but when you did all leaves,
Mm-hmm.
was this per graph or for the whole forest?
Now it's per graph. That's a good question because it's called here. So for tree in forest, then all leaves equal get leaves, right? So it's called on the tree level because queries work with graphs, right? Yeah, it's on the tree level, right? Yeah. Yeah, so rewrite is the VPL function that executes the rules inside the tree. So the one thing that and I said that last time also, the one thing that I don't allow you to do is run the rules, because I want to ensure that the rules are run in this notion of parallel, right? Huh? Yeah, I use rewrite. Yeah. Before I had elongate and rewrite, and now I replace elongate by all of this. Yeah. And then, so yeah. Yes. A function is a function, yes. No, a query. A rule in a query. Yeah, so a query retrieves nodes, graph nodes that match a particular condition.
Yeah.
A rule retrieves those nodes and replace them
Yeah, yeah,
with something else. And it's a creation of organogenesis, basically creation of organs.
yeah,
You do it with rules.
Yeah.
Queries is to basically modify the internal state of those organs.
Yeah.
So that's always going to be related to the F in FSPM, basically. Yeah. So once I have defined all the components of the model, and so I was in the section model definition, then I do a particular simulation, right? And you can imagine that this will be like a separate script. All the previous code could actually be in a package, right? And then a separate script, then you initialize. In this case, I have different relative growth rates. So I do a little histogram. I have, again, different orientation, just like before. Okay. I have different origins. So this is like the previous forest, right? And then I have a create tree function that is a little bit more complicated. Okay. Because basically I need to compute the initial dimensions of the leaves in the internode for the initial biomass of the leaf and the internode. So this is always like when you initialize the trees, you often have to call some of the functions that you're going to call in the daily step because you have to do some of the same functionality, right? Because otherwise, if I allow you to give dimensions and biomass as input, then you can end up with plants that are not consistent, right? And then it's the same. So I create the rules, but now the rules have the parameters for the leaf and the internode. So the initial biomass and dimensions, and then the axiom with the origin orientation, and then the graph with the parameters for that plant. So this is basically like what we saw before. Okay. Create a tree. And in this case, I basically do the first option that I gave you about the soil. So I create a graph for the soil. And that means I create a type soil that inherits from virtualplant.node because it's going to be in a graph, right? Then I create a feed function that defines the color of the soil basically as a rectangle. And then I specify the creation of the soil in the axiom. And of course, there are no rules because I just want to create the soil once and leave it there, right? So this is basically exactly what I was doing before with the rotate and the translate. But now instead of manipulating the geometry directly, you let a turtle do that for you, right? I create the soil, and this is how the soil looks like. So just a rectangle there, okay? And then I create a function for the rendering that will take my forest and it will take my soil, put them together, and then render the whole scene, right? So in this case, what we're doing is we basically have an array of graphs representing plants plus an extra graph representing the soil, and we can merge the scene together. So that's also something you can do. You can generate multiple scenes and then merge them together. Yeah. So it's a different way of doing it. Then what do I have here? Yeah, here I was showing how you could compute the LAI, okay? Because I thought, maybe that's interesting because very often when we work with our models, we want to extract information at the canopy level, which means that you're not working with individual plants, right? But you're working per square meter. But in this case, it's very easy because we just loop over the trees, over the forest, and then we extract the leaves, and then we just add up the area for all the leaves. So literally here I'm looping over all the trees, over all the leaves of the trees, and then add in the leaf area, and then I know this is something you will have to change manually if you change the settings, right? But then I know that in this case, I'm simulating 400 square meters, right? So then I get the LAI. Yeah. Right, so you can also then retrieve, you can calculate properties of the canopy itself, but just aggregating data across the different graphs. This is similar as before with the trees. Yeah, rendering the forest, let me see. Right, because they're super tiny. Actually, I don't know if there's anything in there yet. There is something, no? Okay, because my screen's also not very clean, so I don't know if it's that is something. Oh yeah, there. I saw it. It disappeared. Yeah. It's so tiny that it's probably just clipping with but now here I'm simulating 50 days of growth, done, a render, and then you get these little drops. And these trees don't look so nice, actually. But that's, yeah, you will have to tune the sync strength and the relative growth rate and these kind of things to make them look nicer. Yeah, pushes. Yeah. But you can still see there's differences. Like this one's smaller, this one's bigger, because of the difference in the relative growth rate and toxicity and so on. Okay. Yeah. So basically the template for building the model is still the same, right? So we define the types, we define the feed methods, we define the rules. Now the rules are getting more complicated, and then we have a bunch of functionality, and then you can define all these functions to do usually a combination of functions and queries to do all the functionality and also the integration over time. Okay. You can get the LAI, and then it gives you this very tiny LAI. Okay. What do we have left that maybe we can cover today is an RUE driven forest. So this is the same model as before, but now instead of having a relative growth rate, we have a reduced insufficiency model. So now we're going to use the ray tracer. But maybe we take a small break if we move into this. Yeah. But at least I'm going to show you a little bit how the ray tracer works and how it will fit in this template that we have created so far. Okay. So when you're using the ray tracer, there is a package that is part of what I call the VPL verse, the VPL universe, okay, which is not, let's say, is not imported by Virtual Plan Lab, so it's technically not part of VPL. You don't need it to build an FSPM, but it's very useful, right? So those are the VPL verse packages. So one of them is the Sky Domes, used to be called Sky, but they make me change the name because they have a rule in Julia that packages should have more than 3 letters in their name. So Sky Domes is basically going to create the light sources if you're simulating the sky, okay, for your ray tracer. But we need to use that package. So this is going to be the same as before. The main differences is that, yeah, the only difference I'm going to highlight is that now inside the internode and inside the leaf, I have a new type of object material, which is of type Lambertian, right? And this is an object that defines the optical properties of the organ, and it will also store the absorbed power. Okay. So you have Lambertian, you have sensor, you have a black object, so absorbs everything. You have a Fong type of material, and here, because I assign it one value for transmittance and one value for reflectance, so here we see the Unicode. It means that we're going to be simulating just one type of light, one wavelength or the whole part or something like that, right? But if you give it multiple values, like an array of values, then that allows you to simulate multiple wavelengths or multiple wavelengths, right? And there is no restriction in terms of the number of wavelengths that you simulate. So you can do as many as you want, okay? It's just that you're responsible for keeping track which one is which, right? So you can have far red, you can have red, green, blue, thermal, whatever. Okay, so we're gonna need that for the ray tracer. And the rest is pretty much the same thing. That's it.
You'd better save it.
Yeah. I will forget. Won't get to this. So we have the same. The feed this is the same as before because we're not changing development. So we just rerun this code. Line interception, right? So now we're going to calculate line interception. So to compute line interception, you're going to need to create a scene. The scene is the same that you use for visualization. It's just that instead of determining the color of the components in the scene, you determine the material. And so there's going to be a second argument, and that's the one that is relevant for the ray tracer. So here we have the creation of the scene. Here I'm using the soil, not in the graph, but using the manual manipulation, just to make it different. But then I'm creating a soil material object. Okay, Lavertian with an albedo of 21%. So when I add the soil to the scene, I specify material equals soil material. For the graphs, you will do this in the feed methods. Right, so now in the feed methods, I specify the color and I also specify the material that is stored in the graph node. Okay, so that's the only difference. So we want to use the ray tracer, then you need to assign a material to that object. Every mesh that you add to the scene needs to have a material associated to it. Okay, and this. Now I'm going to talk about the sky, and this is not updated. This is actually not going to run. But okay, we ignore that. Basically here I'm missing the actual angle of the sun. That is not specified in this code, but there is a way to do that. The idea of the Sky Dome package is that it helps you with different calculations related to solar radiation. So it helps you to compute things like day length. It helps you to compute the solar radiation that you will have for a clear sky. So you give it latitude, the day of the year, and then F is like fraction of the day. So 0 will be sunrise, 1 will be sunset. And so you can partition the day. Yeah. Sorry, so these are generally different fractions. And then you're looping over the fractions. Yeah, sorry. But you know what I mean. And then the clear sky function will give you the total global solar radiation and then the direct and diffuse radiation that corresponds to the time of the day of the year, and the latitude. And it also gives you the angles of the sun, like the zenith and the azimuth, which I'm not using here. But you can, right? So it gives you that information. So this is like classical astronomical equations. It can also help you with conversion, because by default, what you get is in watts per square meters. Okay. But you can modify it into either power or flux. So flux will be micromoles per square meter per second. Okay. And you can also convert this, because this is total solar radiation, you can convert it into par or near. And in the future, I will add conversions for other things like far red. Okay. And that depends on direct or diffuse. So this part is just based on some reference calculations that I did many years ago. You don't have to use it. You can use your own coefficients like 0.45 to convert into par or whatever like that. Okay, this is just to help people because I document what I got it from and what it means. Okay, but you don't have to use it, right? So yes, you can. It's up to you to keep track of this. So in this case, you only have one, which is going to be par. But if you have red, green, and blue, then you can calculate the conversions to red, green, and blue. And then when you give the sky function, in this case, the diffuse light, you need to give it 3 values. And that will be diffuse light in red, green, and blue. And then you need to make sure that in the material you use the same order. And that's what I mean that you need to keep track of it. Okay. So this is optional, but it can help if you don't remember the coefficients, right? And basically the big function is this one. So the big function gets, you can specify the direct solar radiation, and in this case, no. You can specify also, which I don't show here, the angle, so theta for direct solar radiation and phi, right? So you can specify these angles, which you can get from the clear sky also, okay? Otherwise, by default, it assumes that the sun is at the top of the sky, okay? You can also specify diffuse light, okay? The number of rays that you use for the diffuse light or for the direct light, okay? So if you look down here, here is specified the direct light, here is specified the diffuse light, and so you can build the domes incrementally. You can first do the diffuse light dome, and then you can add the direct light sources, okay? And for the diffuse light, you can specify how many light sources you want to use, and that's by dividing the sky into different angles, zenith and azimuth, okay? And 2 more options that you have. One is, how do you do the discretization? Don't worry about this. Normally you want to do equal solid angles. It's like a very technical thing. And what kind of diffuse light model do you want? So you have the standard overcast sky, you have the uniform overcast sky, and then you have like this CIE standards, right? Most of the time, for cross simulations, people go for the standard or the uniform, okay? And this is basically telling you how diffuse light varies with the angle in the sky. So I already did all the calculations in the package. So basically, the way you create the dome is that you calculate the diffuse and direct light. At the moment, I only do it for clear sky. If you have actual solar radiation, then in the future I will have an option to use the actual measured solar radiation, because that affects the amount of diffuse light, of course. So those calculations will be there. And then you can specify how many light sources you want for the dome. And for the direct light, you can do it for different time points, right? So basically, this function is calculating the dome that we use in many of our simulations, where we have diffuse light and then we have an arc of direct light sources for different time of the day. Yeah. So you do need to know the different functions that you need to call and how to pass the information to these different functions, but all the actual geometry and all the astronomical calculations, like how do you calculate the azimuth of the sun and these kind of things, they're done for you by the package. Okay, and this is tested, documented, so you can read the documentation too. So direct light sources are by definition at an infinite distance. So what I actually do, and yeah, this is something I have to mention, the implementation that I have is that the direct light sources are special because they don't have an origin. So they're generated from the top of the scene. So the bounding box of the scene scales with the size of the scene. This does mean one thing, that it only makes sense to use directional light sources if you have the grid cloner active. Okay, so if you want to simulate isolated trees, you would actually need to simulate like a big scene with a tree in the middle. Yeah, because otherwise you don't get the correct results, right? But it really simplifies my life, and I can make sure that it works correctly. Well, we already made sure that it worked correctly after some iterations. But yeah, they're generated on the top of the scene. Yeah, and you can specify different number of rays for the diffuse dome and for the reg light sources. Okay, I think that could be interesting. Yeah, sorry, this is when you have an integer number. But so basically, if I say this, so this is an integer, it's not a floating point, but then it's hard to see how many zeros you have. So you can use this underscore to separate the thousands. And this will be, this is exactly the same number. Okay. Now, if you use a comma, then it thinks it's something else. Yeah, but it will be like the comma separator. Yes, it plays the same function. So this dome, actually, it's a collection of light sources that you can use in the ray tracer itself. Okay. So now, how do we create the ray tracer? So the ray tracer is going to take several inputs. The two that are compulsory are the scene and the sources. So the sources are the light sources. So they could be the dome that you created, but also any light source that you want to add manually. So you can simulate LED lamps, you can simulate an LED tube. So I allow for aerial sources, light sources, point sources. You can change the angle of the sources, all these kind of things. Okay. But for people who are mostly doing greenhouse without supplemental lighting or field, you just go for the dome. And the 3D scene, as I said before, is the same as for visualization. It's just that you need to specify the materials. Okay. Now, if you want to change the settings of the ray tracer, the number of rays that is in the light sources, so when we create the domes, we decide the number of rays. But here you can specify the grid cloner. So basically, nx and y are the number of clones in each direction. Okay, so you can create clones in the x, y, and z direction, so vertical clones. And then the x and the y is the distance at which you generate those clones, right? Yes. Yes. I mean, that could be like a vertical farm, I guess. I don't know, like they're on top of each other. Yeah. Yeah, yeah. The light affects the one on the top. Yeah. I don't think it makes sense for the field, but it's trivial to add it. So I don't know. Maybe people with an urban garden, maybe you have like different crops growing on a trellis. I don't know. So the dx and dy are the distance at which you generate the clones. Okay. And that is calculated from the distance between row or the distance between rows. Okay. I recommend that you specify it because by default it will use the bounding box of your scene, but that is not the correct one because you can have plants growing beyond, you can have plants growing into the vital space of the next row, right? And you want to create a new clone so that it overlaps. Yeah? So the neighboring rows can overlap their leaves, right? So that's why you need to specify this. I have because I realize this is not entirely clear how to do it, so I have a guide with an example of how you would create a scene with very simple plants, right? But I show how you could do the grid cloner for a specific planting pattern. And yeah, that's basically it. So you can turn parallelism on and off. So by default, it doesn't run in parallel. So if you want to run in parallel, you need to say parallel equals true. Okay. And then there are other settings that you don't need to worry too much about. It's just like technical stuff. It's for performance. But there's a way to tune the performance of the ray tracer by playing with some of these settings. Right? And when you want to run the ray tracer, basically you create the scene, just like we did before, from the graphs and the soil. you create the light sources, in this case using the sky domes. Then you create the ray tracer object, and then you call the function trace, okay, with exclamation mark. So when you call the function trace, that will run the ray tracer, okay? And what it does is two things. First, it resets the absorb power of all the materials to 0, and then shoots the rays, and the new absorb power will be accumulated in those materials, okay? So these material objects are the ones that you assign when you create the scene, and when you use the feed method, for example. Okay, so it keeps a connection to the original object. So if you now want to retrieve the absorb power, you need to go back to the graphs, to the leaves, and then extract the absorb power from those materials. Okay. I'll show you here an example. Yeah, so here we just focus on the part of the code that is relevant. So it loops. So I've run the ray tracer. Okay. Here's where I run the ray tracer, and then I loop over the trees. I extract the leaves of those trees, and then I extract the power stored in the material of those loops. Right? Okay. Yeah, because also the material object, so because you can have multiple wavelengths, it's always stored as an array. Even if you only have one wavelength, then basically it's an array with one value, right? It sounds counterintuitive, but otherwise you get into trouble. Yeah. Exactly. And then the rest is basically the same, except that now we will calculate the biomass from the absorbed light. Right, so this is the same as before, the same as before, same as before. And now, basically, we calculate the par first when we run the ray tracer, and then in the grow function, we extract this par times RUE, and that gives us the increment in biomass. And the rest of the code is the same as before. Okay. So with the ray tracer, you have total control because the ray tracer is total control. You own the object that contains all the information for the ray tracer. So that means several things. One of them is that you could have multiple ray tracers in the same simulation. There could be reasons why you want to do that. I still need to think about whether it makes sense, but that's a possibility. And yeah, you can programmatically change all the settings of the ray tracer. It's all fully exposed. You decide when the ray tracer runs. And so like, I don't know, when people simulate trees, they're always trying to speed things up. So maybe you only run the ray tracer once every 10 days. Calculate line interception, and then you assume the same line interception for the next 9 days because it's too expensive. I don't know, something like that. You can run the ray tracer multiple times within the day. You could run a ray tracer for diffuse light once a day, and then different ray tracers for direct light at different times of the day, right? So you have a lot of freedom in how you use the ray tracer. Because, yeah, basically you own it. All the objects, and you can have multiple ray tracers in the simulation. The only disadvantage that, yeah, it's not as fast as I would like it to be. So I still need to figure out how to improve the performance or find someone to improve the performance. And that can be a bottleneck at the moment. But otherwise, yeah, it is multi-threaded, so it will scale with number of threads. Yes. So that's the max iter. So max iter is the maximum number of iterations. What happens is that it would always bounce 4 times unless it leaves the scene, right? And after it bounced 4 times, then a ray may or may not die, and this is probabilistic. So there's a probability that the rays kill, So this is called a Russian roulette algorithm. So if you say probability of 9.9, that means 90% of the time a ray that has scattered 4 times or more will be terminated. Right? So at the moment, I think there are problems with memory. For some reason, it's not scaling very well with the size of the scene, like the number of triangles. And yeah, if you have a very high number of iterations, then of course it takes longer. Yeah. But yeah, my gut feeling, I don't know exactly what the problem is, but my gut feeling is that the ray tracer could run faster based on what I see in other ray tracer, but I still need to figure out what the problem is. Yeah. And indeed, it's not a very, like if you increase the complexity of the scene, it doesn't go smoothly up in time as you would expect, or the number of rays. Like there's some breakpoints in the performance which suggest that there's some issues with maybe with the memory consumption. So hopefully one day the ray tracer will be more competitive. Yeah. I don't know if it's much lower. Yeah, you need to get used to a few seconds, several seconds, for like 10 million rays, I think, right? Yeah, that's the thing, that somehow is scaling with the number of triangles in a way that it shouldn't. I need to figure out why. Right? But it's also, we haven't also explored, like, because this kind of settings, this acceleration and rule, this has an impact. So I haven't really have time to explore what are good settings for the ray tracer, what are optimal settings, and so on. So if you're defining a stem, I would say give it a transmissivity, so that's the tau of 0, and then give it some reflectivity, right? Because that determines if the transmissivity is 0, then it cannot go through. Yeah, that's the idea. So you can do sandwiches if you want. In the future, and I actually had at some point, but I turned it off. I want to have what I call a side switcher, because I know which side of the leaf is being hit. That I know inside the code. So it's just a matter of having a material that can store the power separately for light rays that hit from one side or from the other, because that information is available. But I need to implement the material, the type of material that will do that, and then you can separate the light intensity from both sides. Yeah. Now, for all the materials, it doesn't matter. Yeah, I know. I think I ran out of time when preparing this tutorial, and I was like, okay, I don't know what the parameters should be. You also run it for very few steps, right? I think the experience that when you start doing things that you want, then some things will not work. So I do have to give the warning. But I'm usually also relatively fast in fixing them. Like if you find a bug or something doesn't work, I can usually fix it within a day. Yeah. Yeah. But I think all the big problems, because now we have an intercrop model that runs okay, I think. Yeah. So I think all the big problems we caught already, many of them related to the ray tracer actually. But yeah, I have to admit, of course, there might still be some issues. So you always need to double check more with this than growing. Double check that the numbers make sense.
Yeah.
Numbers make clone clones the scene, not the light sources. But I haven't thought about that particular case, because for directional light sources it's different, right? Because this is kind of far away. But I mean, if you want to have the LEDs replicated, you will have to, but I'm thinking whether you actually have to. I don't think you have to. I don't think you should clone the light sources. It will not, because it only clones the scene. But I don't think you should clone the light sources. Yeah. Yeah. Yeah, but we need to discuss about these light sources, because I haven't really thought too much about, let's say, the artificial light sources. Yeah. Any other questions?
Yeah.
Really? Okay.